So students, may I now introduce you to Dr. B.S. Sahayanathan, who is working in the Astrophysics Division of Bhabha Atomic Research Center, which is engaged in setting up very high energy telescopes in India, namely Tactic at Mount Abu and MACE at Hanle in Ladakh. Dr. Sahayanathan has contributed significantly in the area of active galactic nuclei. He has been collaborating with various institutes like IUCA in Pune, TIFR in Mumbai, IIA, and universities like Kashmir University, Calicut University, Tezpur University, etc. I invite Dr. Sahayanathan, and please don't miss this talk. I know we are running a bit short of time, but this will be really a very fascinating talk, and you'll enjoy. Dr. Sahayanathan, please. Thank you.
Good afternoon to all, and thank you to Himal and all the other organizers thank Himal for the nice words. And I should particularly thank the organizers for giving me an opportunity to interact with the young and fertile minds of the country. So, in fact, I would love to have this interaction in real rather than in virtual. Sadly, with times the lifestyle change. We like or we don't like, we have to accept it. Fine, so let us come to the topic. Let's come to the topic of this synchrotron emission in the universe. So, most of the life on Earth sits with the sun. However, for astronomers, there's a time when the curiosity arises, when the sky is lit with a billion and billion of stars twinkling at us, surprising us, and that's how the astronomy began in the mankind. Okay, so, well, for ages, humans were believing only what they see with their eyes. The same was the case for astronomy, and the astronomy, starting from Galileo Galilei, the father of the modern astronomy, the astronomy was confined within the visible energy range, that is the colors bounded by your red and violet of the rainbow. And we were not knowing the universe is hiding from us some beauty, the tremendous beauty of the universe was hiding from us, which is invisible to our eyes, unless some smart radio engineers who transformed themselves into astronomers. It all started after the World War II. So when the radio communications was in the peak, where the different locations on the Earth were being communicated through the radio wave, and after the World War II, these radio engineers who became the experts in the radio communication, they were looking for the avenues where they can utilize this knowledge they gained during the World War time. So, and one such engineer is called Jansky. Well, Jansky was a radio engineer. He was working with the Bell Laboratories and he was involved in the wartime communication. So what he found is, during the communication, there was a steady hiss, a steady static noise when this communication between the transatlantic communication when he was dealing with it. So he found this constant noise and he decided after the war is over, so let us try to understand why this noise is coming up. So what he did is he built an antenna, and the antenna was placed on a turntable, which later on given the name as Jansky's merry-go-round. So he rotated the table to find out what is the origin of the hiss or the static sound which was disturbing the communication. So as usual, like everyone, he was suspecting about the terrestrial noises, and he tried to look into the thunderstorm and various other options which can disturb which was the possible sources which can disturb the radio communication, and all his queries were coming as a wrong, and he found this was not the case. It took time for him to realize this is not the noise coming from the terrestrial, somewhere else outside. And that happened with a careful observation. What he found is a diurnal steady hiss. What is it? The radio noise, what he was seeing, what he was receiving in his receivers, it peaked during a day, 1 24 hours day, and then it decayed. So naturally, every one of us, if it are given something which is peak in a day and goes down, the immediate thing we associate with the sun, is it probably what he was thinking the radio noise coming from the terrestrial? It is not from the terrestrial. It may be it's from the sun that is creating this noise. So then he started looking. It took nearly for a year for him to identify this noise. So then he started his observation again to find whether the noise is coming from the sun. And to his surprise, there was opposite. When the radio signal peaked and when the sun was in the zenith, there was no matching. And not even that. So if it would have been due to the spin of the earth or from the sun, then the two peaks, the time period between the two peaks should be separated by 24 hours. Incidentally, he found that peak is not constant. It was less than 24 hours. The time was kept changing. So then these two things gave him an idea. It is not probably from the sun, something other than the sun. And then he came to an idea that then he thought, when you have a careful look, then he found the strong radio signal what we are receiving is from the entire Milky Way galaxy what we saw. Well, now this is interesting. Suppose, for example, our eyes, if a human eyes were not tuned for the visible light, and if we are allowed to see the radio waves, our day and night would be decided by not by the sun, rather by the center of the galaxy. Because the galaxy was so bright in radio, and the sky is so bright in radio, so we would have probably decided our day and night with the center of the galaxy. And of course, the time is going to be much complicated because we are going to revolve around a dull star, placing our clock at the Milky Way galaxy. So, well, I wrote there the sidereal time. I advise you people to go back and study what you mean by sidereal time, why the time is complicated. Okay, fine. So, and this was an interesting discovery by Jansky, and this was the first ever radio observation by humans. So this one. And sadly, Jansky wanted to continue this work further to build better telescopes to confirm this radio signal is indeed from the Milky Way. But the Bell Laboratories, as usual, when you want to write for the fund, he said no, he wanted a fund to identify the radio noise. So the Bell Laboratories rejected his proposal and he didn't give him fund, saying this static noise is so weak, we don't need to spend this much of money to identify it. So poor Jansky, he stopped the radio astronomy with that. Okay, and then for 2-3 years, there was no one to continue this radio astronomy until an interesting person, Grothe-Reber, came into this field. Grothe-Reber was very interesting. Grothe-Reber was a radio engineer by profession, and he was an amateur astronomer. So he came across this Jansky's work, and he found this is the work which was actually he wanted to pursue because he was a radio engineer. He was good at radio engineering, and he found, and he is an amateur astronomer. So he started, in fact, he applied for Bell Laboratories to work with Jansky. Of course, already the Bell Laboratories stopped Jansky to work on, so they rejected his application. So, the Grothe-Reber was so determined, so he decided, no, he will go for it. He started building his own radio telescope at the backyard of his estate. So that was the first parabolic radio telescope which was built by Reber on the backyard of a telescope. So that's why you say the first radio telescope was actually built by a private, that took by an individual man. Okay, fine. So what the first thing he did is he confirmed the radio signal detected by Jansky is indeed from the Milky Way. And he showed the world, yes, the Milky Way is so bright in radio. And he didn't stop with that because he got a better telescope than Jansky. It's not an antenna. He had a parabolic dish, so he can focus at a different point in the sky. So what he did is then he started scanning the entire sky and produce a radio map. And he found not just the Milky Way, there are many radio bright spots were in the sky, and he called, it was thought to be radio stars. There are stars in the Milky Way which are very bright in radio. In fact, I like to mention the Weber, when he was getting into this radio astronomy, so he used to tell the astronomers don't believe in Jansky because they don't know about radio. And the radio engineers never bothered about this because anyway this noise is a very weak. So it needs some person who is interested in astronomy as well as a radio engineer to look into this radio astronomy seriously. In fact, for nearly a decade, Weber was the only radio astronomer in the Earth. He didn't stop. And in fact, his publications were not published in Astrophysical Journal because the Astrophysical Journal, the top journal of the time, they decided how to publish it. This is not an astronomy work. So he has to first publish his works in an engineering journal and then go repeat it for the astronomical journal. So this was a struggle Grothe had to encounter to bring, to show the world the universe is communicating with us in radio. That's the invisible, which we were not knowing about it. And even after that, so what happened, he found out that then the many radio engineers and the astronomers got interested in the observations by Weber, and then many people came into it. Still, it took 2 decades to identify, okay, yes, of course, the Milky Way is emitting radiation and there were different radio stars. What is the process by which the radio is emitting? And it took 2 decades for the people to understand. It is first by Alvan and Herlofsen. So in 1950s, he explained the radio emission from the radio stars. About these radio stars, I'll come again in a short while. About from the radio stars is to synchrotron process. And immediately, that idea was picked up by Keppenhuber in 1950 on the same year. He got the cue from the Alvan and Herlofsen work, and then he picked up that idea, and then he estimated the radio background, the glow, it was there in the universe, in the galaxy, and he estimated that from this cosmic ray spectrum, electron spectrum, and he showed that's also due to a synchrotron. I will come back to synchrotron in a short while. So this is what how the radio astronomy is the first astronomy which showed the humans the universe exists beyond the visible light, and rather the universe was hiding most interesting and the exotic phenomena which was not understood in our visible region. Well, so so now we know that so the universe is lit by the synchrotron radiation in radio rather than more than the other wavebands. Fine. Well, and today, even though the radio astronomy had a lot of struggle to establish as an astronomy, today the radio astronomy is a far superior in resolving the solving detailed astrophysical objects. You may be aware of a few years back, there was a telescope, Event Horizon Telescope, which took a snapshot of a black hole. So I will come to that later. And this telescope have an resolution of micro-arcseconds. If you want to compare an equivalent, that means the telescope can can pinpoint a chocolate wrapper on the surface of moon. That is the resolution this telescope can see. The highest resolution ever human can achieve. So it was, because it was almost take the whole Earth as a telescope, the size of a telescope is the size of the Earth, and that is the resolution they have achieved. Well, in the right side, I have put up the radio telescopes in India, because in India also there were a lot of initiatives came up to build up the radio telescope, thanks to Professor Govind Swarup, who was the main person behind this radio astronomy in India. In fact, he founded the National Center for Radio Astrophysics at Pune, and he was the main backbone of this finest telescope, Giant Meter Wave Radio Telescope, which is situated close to Pune. Sadly, Professor Swarup passed away on September last year. Well, what he started is going to survive for long. Fine. Okay. So now, so radio was the first astronomy which ventured into the invisible region and showed the humans, of course, the universe is having a lot many information in the invisible region also. In fact, it was not the radio astronomy. It was an infrared astronomy. Infrared astronomers were also trying to convince the astronomers the universe is bright in infrared and we can get a lot of information. The astronomers never believed them. They were all seen as an, what do you call, as some engineering tactics or something. So after Grothe and Reber showed the radio universe is bright and very interesting, then the people took a serious note of the infrared astronomy, and the infrared astronomy started budding up again. And then, they didn't stop with that. They went into the even other wave bands like X-ray. So initially the X-ray astronomy was born in around 1950s. So what they started is, they started with the sounding rockets. What are rockets? They had rockets, and they put up the calorimeter or scintillation counter, whatever you have. They put it on the rocket and they send in the space, not in the space. They launch the rocket, it goes and falls down. During the trajectory, it collects an amount of X-ray data, and they try to analyze and try to find the X-ray, how the X-ray emission from the universe is happening. But of course, there is a drawback because the rocket survives only for a short time. So he wanted for longer observation. So then they started using balloons. They loaded the balloons with calorimeters and scintillators and sent it to the top of the atmosphere to observe the X-rays. Okay, I forgot to tell why they have to send rockets and balloons is because your atmosphere is opaque to X-rays. So if you want to see the universe in X-ray, you have to go out of the atmosphere or top of the atmosphere. Then only you can see the X-ray. Otherwise, the X-rays will not reach the ground because the universe will be, the atmosphere will absorb the complete X-ray. Fine. So today we have satellites. They send the X-ray detectors on the satellite, and they orbit around the Earth, and then we can have a continuous observation of the astrophysical sources in X-ray. So here I have written the Uru, that is the first X-ray satellite sent by NASA in 1970, and in the left I have written, shown the AstroSat, that is a telescope launched by ISRO on 2015, and this is not just an X-ray telescope, it's a multivalent telescope. It can see the universe starting from UV to X-ray. So what you call even a hard X-ray, almost the entire X-ray band it can observe. And this is now, it is still operational and producing wonderful results. If you remember in yesterday's Dipankar's talk, he showed some light curve from our satellite AstroSat. Fine, so this is how slowly the astronomy started deviating from the visible region to the invisible region, and we started gathering more and more information from the radio and X-rays. Fine. So, well, in the X-ray, one of the important input from the X-ray astronomy is, what they found is, in the galaxy, most of the supernova remnants, they are the remains of a supernova explosion which happens in our galaxy. They emit in X-rays, and that X-ray is also by synchrotron radiation. Even not with the galaxy, if you go beyond our galaxy, there are other galaxies. Most of the X-ray emissions we observe in the outside our galaxy, they all come from they are due to the synchrotron radiation. Fine, this is what we know it. So now, let us come back to the basic. What do we mean by a synchrotron radiation? Of course, for last 1.5 days, we are hearing about the synchrotron radiation, and of course, there are a lot of experts who explain about the synchrotron radiation. So let me put it in a very simple way. So synchrotron radiation is produced when a highly energetic charged particle, say it a proton or electron, whatever, when a highly energetic charged particle moving with the speed close to the speed of light, when it enters the magnetic field, it gyrates around the magnetic field and it emits. That's what your synchrotron radiation is. Fine. Well, so then for a synchrotron radiation to produce, I need two ingredients. One is the magnetic field and another one is the high energy charged particle. So if you have two ingredients, then you can produce a synchrotron radiation, and the radiation can extend from radio to gamma rays depending upon the energy of the charged particle as well as the magnetic field. If the charged particle energy is very high, or relatively high, it can emit in X-ray, Or on the other hand, if your magnetic field is also strong, it can also emit high energy particle or high energy radiation. So fine, so this is what the ingredients required for the synchrotron radiation. Well, so now let us look in the universe whether these ingredients are available. Let us first have a look at a magnetic field. Of course, we know our Earth is having a magnetic field. Earth is actually a magnet. Of course, it's going to have a magnetic field, not just Earth. If you see the sun, which represents the typical stars, all the stars have their own magnetic field. So of course, stars also have magnetic field, and even the dead star, which becomes a neutron star or a pulsar, rather the dead stars have the most strongest magnetic field ever we know. So in fact, Dipankar also spoke about it yesterday, and even in the video what we saw in the beginning, there also we saw about these pulsars and neutron stars having a strong magnetic field. And why only in our galaxy? You go out of the galaxy, you see every galaxies have a large scale magnetic field which extends up to millions of light years. So we have the huge magnets in the universe which is all moving around. So there is no shortage of magnetic field. Of course, the first ingredient for the synchrotron radiation is ready. We have the magnets. Now let us go for the next ingredient, that is the high energy charged particle. That also we know our Earth is continuously bombarded by high energy cosmic rays. They are charged cosmic rays. Of course, that gives you the universe is filled with charged cosmic rays everywhere. So we have the second ingredient for the synchrotron radiation also. So the synchrotron radiation has to be omnipresent in the universe, because both ingredients what is required, it is there in the universe. Well, fine. So now we know the synchrotron radiation is everywhere. That's omnipresent in the universe. It is one of the important radiation which is emitting in radio. All those things we know it. So as I mentioned about the radio stars, let me come back to radio stars again and see how this synchrotron theory helped us to understand what is this radio stars are. Interestingly, after Grothe found out those radio stars, then the optical spectroscopy techniques improved very much, and the people were able to identify the lines. It was Silver who found the lines of this radio star. They are redshifted. And at the time only Hubble was also there. Hubble gave the idea of the redshift is connected with the distance, and then immediately were able to identify these radio stars are not really stars, because the radio stars, they are at so far away distance, they can't be within our galaxy. They are so far. So then it has to be a different galaxy. So what the people thought as a radio star is not a star anymore, rather it is a radio galaxy. And now this is a very interesting point, because you said some light is close to me. You assumed a light which is close to me and the light is bright. Now someone says the light is not close to you. The light is very far away from you. And now you say, then you question, oh, still it is so bright. Then your question comes, that means that light has to be extremely powerful. So what took, and this question was asked by Babbage, and what he used, so let me assume these radio stars are the radio galaxies at far away distance, and the theory says the radio emission is from synchrotron radiation. So let me calculate what is the energy of this radio galaxy. And he got an alarming number, that's 10 to the power of 60 Earths. Why this number is alarming is, this energy is so powerful, you take two Milky Way galaxies, you merge together, combine the entire gravitational energy, still it would barely explain the power of this radio jet. That means that is the power of the radio galaxies. So this idea, when the Babbage said this is what the minimum energy of these radio galaxies, and then it raised the eyebrows of all the astronomers, how this much of energy can be produced. Finally, the question was answered by Hoyle and Fowler. What he said is, at the center of the galaxies, we have supermassive black holes which has a mass of typically 1 billion solar masses. The origin was not known for quite long. Recently, from the gravitational wave studies, we have this stellar graveyard. Now we have a rough idea about how these supermassive black holes are created in the universe. But what Hoyle and Fowler showed is, so this radio galaxy should have a massive black hole at its center, and the gravitational potential due to that black hole is responsible for the huge amount of radio emission which we see. Well, and so, and as I told you, so one such image of one such black hole is being shot by the Event Horizon Telescope from the radio galaxy M87, which happened some few years back. It was a big news article. So you all must have heard or seen this image quite often, which looks like our typical Medu Vada. Fine. So, well, so this is how. Okay, and this is what. So all this, till the image we reached here, everything goes back to the radio astronomy. If we have not known the radio astronomy, we wouldn't have reached up to here. Because the radio astronomy is the one which, well, say I could have said that also, because what Grote Reber started with the parabolic disk. And then what happened is, then the new technique of radio came was interferometry, which was started by Ruby. She was the first radio astronomer, Ruby with McCready and Powell, I think. Okay, these are three people who started in Australia. They started this interferometry technique by which they're able to resolve the astrophysical sources in a very fine detail, and that technique led to the construction of Event Horizon Telescope. Finally, we were able to take a snapshot of the black hole of a radio galaxy sitting in the center. There's an M87 radio galaxy. Well, fine. This is a one story, how a synchrotron theory helped us to understand the physics of the astrophysical sources. Another one is, well, it was rather more a confirmation. What they found is the galactic radio background. So the idea is, so you have a galactic radio background. Now you know the cosmic ray electrons are there, and the galactic magnetic field is also there. So we have three quantities. If you remember, I said for a synchrotron radiation, all you need is magnetic field and a high energy charged particle. So we have a galactic magnetic field, we have the cosmic ray electrons, it's going to produce synchrotron radiation, that is going to be the radio. And now we have the radio observation, which gives me the radio spectrum. Now what I do is, I take the radio spectrum, and then I observe the electron spectrum, cosmic electron spectrum, then I know what is the typical magnetic field of the galaxy, so I work around and I predict what should be the radio spectrum produced by the cosmic ray electrons and how they match with our the radio observation what we saw, and that's what the image I showed in the right. So that is the observed radio spectrum, and this is the predicted radio spectrum, which is from the cosmic electron population, which I gave in the left. Okay, so and you can see they both very closely matches. So this is another one. In fact, it was very, though I have not gone more detail into it because it's a very important plot. The reason is the cosmic ray electrons, what we receive on the Earth, they have already undergone significant synchrotron radiation losses. The energy has reduced significantly because of synchrotron radiation. So we don't have any idea what is the energy of the cosmic ray which was originated. So now by mapping this radio, and when I confirm this is the radio spectrum is what which is created, so then I can do the back calculation. I give you the radio observation, I give you the magnetic field, so you know this electron spectrum. Now you can account for the energy loss rate which has happened, then I can actually work back and find out the energy of the electron which is being initially produced in the accelerator sites. Well, okay, now, so what this synchrotron theory told us is, what it's telling us is, so the universe is filled with highly energetic charged particles, say it's electron, proton, whatever. What we are sure is the universe is filled with highly energetic charged particles. So then the question comes how they are produced. So there must be some accelerators sitting on the universe which is accelerating this charged particle to such a high energy. So now the question, how am I going to probe that accelerator? So the one clue what we have is, so if in the universe, if there is an accelerator which is going to accelerate a particle to such a high energy, so it will involve a lot of high energy process. So it won't only a synchrotron radiation, there can be other radiation mechanism also, maybe a nuclear emission or other emissions what we know. I'm not going into it, something like a Compton emission. There are many other radiations. Those emissions may not be on X-ray or may not be on radio, they may be in the high energy gamma rays. So basically, if I start studying the universe in gamma rays, it will give me an idea where are these cosmic accelerators in the universe which is accelerating the cosmic rays and which is causing the entire radio background and the radio star, all the stories. So now the approach is, let me try to look for the cosmic accelerators, and that demands the gamma ray astronomy. So Baba Atomic Research Center is building one of the largest gamma ray telescope at Hanley. It is in fact the highest altitude we have. So it's at Hanley, and it is right now on the technical runs. We are not yet started the science runs, which is going to happen very soon. So, and then we can explore this universe in the gamma rays also. Thank you.
So thank you very much, Dr. Sahayanathan. And now we can open the session for a few talks. Those students who want to ask any question to Dr. Sahayanathan can raise their hand in WebEx.
Mr. Sanket Jagdale, you can unmute yourself, come on video and ask your question. Mr. Sanket Jagdale. If Sanket is not able to ask, Mr. Ayaz Khan. Ayaz, you can unmute and ask your question.
Sir, sir, my question is on microwave background. Sir, the microwave background is the image of the previous universe when.
Ayaz, you are not audible. Ayaz, you are not audible.
Hello.
Yeah.
Hello.
Yes, yes. Now you can ask your question.
Sir, the microwave radiation that comes from the beginning of the universe we captured is not actually microwaves when it was started traveling. So when it was started, it was gamma or X-rays, and when it approaches, then it is shifted toward microwave radiation due to red shift. So because of energy difference between gamma rays and microwaves, where does this energy goes? Hello.
Well, I guess I can. The first part of the question I can understand. Probably I may answer. You may get an answer. I'll say something. You may get an answer from here. Yeah. Of course. This microwave background, what we see today is actually start from the Big Bang, Big Bang, which got basically cooled to the region. At that time, it was very high energy. So now it has cooled down to microwave. So in fact, what they call it was a tired radiation. So well, I will tell you some history also. The Grothe-Reber, after his radio telescope, he invented everything. Towards his later years, he was actually wanted to work on this tired radiation. At that time, they used to call this as a tired radiation because it was a radiation of very high energy at the time. Okay, I guess if I'm not mistaken, what your question is, where the energy went, where the energy is lost as it shifting from high energy to radio. So you can't speak in terms of energy loss because this is something of different scale. What happens is it is it is the expansion of the universe. It's the expansion of the scale. Okay, so as the universe is expanding, so whatever the scale, the point is I will give you a small scale, and I take 1 centimeter, and now I am going to expand. Okay, when I expand, the scale is going to change. So whatever the wavelength you saw in the initially, that is very short. Now the expansion has taken, because the expansion of the universe, the scale has been increased so large, what we see as a high energy gamma ray radiation or whatever in the initially, it's going to be shifted to radio in the present universe. So in fact, that's why I said when you are going to look into the radio galaxies, for distance radio galaxies, the light from the galaxy must have originated some light years before, some millions of light years before. The light takes so much of time to reach you. So what the light you are going to see is a light from the younger universe. The farther the object you see, the younger the object you are going to probe. So when you are going to see that time, so if I receive a gamma ray now, this gamma ray is not going to be the same energy as it's emitted from the source. You always add up a factor, what you call the redshift factor. So you add up the redshift factor at the source, this gamma ray is going to be of much higher energy. Did I answer your question?
Yeah, Mr. Gurbaksh Singh. Gurbaksh Singh, you can unmute, start your camera and ask your question.
Can you hear me, sir?
Yeah.
Also, my question is that can you explain the black hole theory again and how human take the picture of black hole? Thank you, sir.
Well, it's not a very straightforward question at this point to explain how a black hole is being created. Okay, you can give a very simple explanations. Of course, it's a wrong explanation. So rather means the moment the usual explanation that people give, you keep shrinking an object or take a sun and make it to a size of a mustard. So at one point of time, it become a black hole. But of course, it's a wrong explanation. This is what explanation you usually find it in a popular level. Is a more involved theory. Rather, I will tell you the second question. How did we able to take the image of the black hole? Well, so what we can see is, what we can find out is the black hole doesn't emit any radiation by itself. So of course, what do we mean by the image of a black hole? What the black hole is going to have is a strong gravitational field. So it's going to attract all the matter towards it. So now as the matter comes closer and closer, because of strong gravitational potential, this matter is going to heat up. And the matter is going to emit a radiation. So what you see is not the black hole, the hot matter around the black hole, which is lit because of the gravitational potential of the black hole. So that's the image we are calling about the black hole image. Of course, the ring what we show is not the image of the black hole, it's the image of the gas which is heated up as it moves closer to the black hole.
Mr. Sahaj Agarwal. Mr. Sahaj Agarwal, you unmute and...
Good afternoon, sir. Are you able to hear me? Good afternoon, sir. Are you able to hear me?
Yeah. Good afternoon.
Please.
Sir, I wanted to ask whether the study can be used to study gravitational waves.
Oh yeah, of course. See, that's what today what we have, the astronomy. See, that's what is all thanks to Jansky and the Weber. We realize astronomy is not confined only with the visible lights. Today we have the astronomy extending from radio to gamma rays, not just the electromagnetic spectrum. We have the neutrino, we have the gravitational waves. So all these things we can explore. It all happened because the Jansky showed the universe is hiding something from us beyond the visible. Yes, of course. That's why I said, I told you at some slide, I told you that the center of the radio galaxy is having a supermassive black hole of mass of 1 billion masses or solar masses. So now, for quite long, people were not aware how these black holes how these black holes can be created, of supermassive black holes. So to a large extent, people have a lot of idea about how a stellar mass black hole is created, say some 1 to solar mass black holes that can be created. How are going to create a black hole of 10 to the power of 9 solar masses? So this answer, in fact, came from the partial answer is coming from the gravitational wave detections. So, and what we right now call it as a multi-messenger astronomy. So the multi-messenger astronomy is to include the electromagnetic observation of the electromagnetic radiation, as well as gravitational wave and the neutrino or even the cosmic rays. You combine all the observations together and draw a global picture of our universe.
Okay, sir. Thank you.
Okay, thank you, Dr. Sahayanathan, for this wonderful talk. And I'm sure the students would have enjoyed this talk thoroughly. Okay.